The proliferation of memes on social media has necessitated the development of sentiment analysis techniques to identify and censor harmful content. To address this challenge, a semi-supervised learning approach is proposed, leveraging the vast amount of unlabeled memes available online. This approach, dubbed Semi-memes, combines autoencoder and classification tasks to effectively utilize unlabeled data. Memes typically consist of images and text, requiring a multimodal learning approach to capture their underlying meanings. The proposed method builds upon the insights gained from contrastive language image pre-training, a multimodal learning technique that has shown promise in various applications. By integrating autoencoder and classification tasks, Semi-memes can effectively harness the power of unlabeled data, outperforming state-of-the-art models on two benchmark datasets: multimedia automatic misogyny identification and hateful memes. The need for multimodal learning is highlighted through illustrative examples from the datasets, showcasing the importance of considering both image and text components in meme analysis. For instance, Figure 1 presents examples from the multimedia automatic misogyny identification dataset, where the text and image components convey different sentiments, emphasizing the need for a multimodal approach. The proposed Semi-memes method is designed to address the challenges of meme sentiment analysis, where the goal is to identify and censor harmful content. By leveraging unlabeled data and multimodal learning, Semi-memes offers a promising solution for social media platforms seeking to mitigate the dissemination of harmful memes. The approach is evaluated on two benchmark datasets, demonstrating its effectiveness in identifying hateful and misogynist content. The research highlights the importance of considering both image and text components in meme analysis, as well as the need for semi-supervised learning approaches to effectively utilize unlabeled data. The proposed Semi-memes method offers a novel solution for meme sentiment analysis, with potential applications in social media content moderation and online safety. In the realm of multimodal learning, detecting harmful content in memes has become a significant challenge. Unlike traditional text-based harmful content detection, memes require understanding and merging visual and textual aspects, making it even more complicated. Manual labeling of data is exhaustive and subjective, leading to disputes and arguments. To address this, a semi-supervised learning approach using multimodal data containing both images and text can ease the annotation process. Recent studies have focused on multimodal content, relying on visual linguistic pre-trained models such as Visual BERT and CLIP. Notably, CLIP, based on self-supervised learning, has been trained on a large-scale dataset and has learned popular concepts of visual and linguistic features, including memes. The hate clip per architecture, which utilizes clip encoders and feature interaction between modalities, has achieved the highest performance on the Hateful Memes Challenge dataset. Semi-supervised learning in multimodal data has been explored for various objectives, such as cross-modal retrieval tasks, punctuation prediction in conversational speech, and emotion recognition in videos. In the domain of memes, studies have attempted to embed images and words in the same space, demonstrating the value of unlabeled meme data. Our proposed approach involves developing a multimodal semi-supervised learning model, consisting of two stages. The first stage involves unsupervised pre-training using the cross-modality autoencoder, CROMAE, which is trained to predict one modality's clip feature from the other. The second stage involves supervised fine-tuning, where the pre-trained encoders of CROMAE are frozen to extract new representations from the original clip features. These new representations, along with the original clip features, are fused to predict the classification target, resulting in the raw and cooked features classification model, RAWNCOOK. The proposed semi-supervised learning approach, called Semi-memes, consists of two stages: cross-modality autoencoder, CROMAE, and raw and cooked features classification model, RAWNCOOK. In stage 1, CROMAE is employed to capture the underlying distribution of each modality. Two CROMAE models, AE image and AE text, are trained separately using the mean square error loss function to reconstruct one modality from the other. Specifically, AE image takes clip features FImage as input and predicts ftext as output, while AE text takes ftext as input and predicts FImage as output. The autoencoders have the same underlying architecture, consisting of linear greater than PRELU greater than linear layers, where all linear layers have the same dimensions of 768. PRELU activation is used to ensure the model learns the negative values of the encoder's output. The CROMAE models are trained using unlabeled data, excluding all labeled data to prevent introducing new bias and variance to the labeled training, validation, and test sets. The latent representations of images are driven by the distribution of the remaining text P, text, which may contain the information of the posterior distribution P, Y, text, where Y is the supervised classification target, and vice versa. In Stage 2, the RAWNCOOK model is used for classification, incorporating both the learned latent representation from CROMAE and the original clip features. The model combines the strengths of both representations to improve classification performance. The authors propose using the Semi-Memes approach to leverage unlabeled data and improve the robustness of the classification model. The authors propose a novel architecture, RAWNCOOK, for multimodal classification tasks, leveraging pre-trained CROMAE models to extract informative features from images and texts. The model takes the encoder part of two pre-trained CROMAE models, freezes them, and uses them to extract latent features from clip features. These features are then projected to 256 length vectors, concatenated, and passed through a final linear layer to learn the classification target. The intuition behind this approach is that the latent features learned by CROMAE on a large unlabeled dataset are informative and can be effectively used for classification. However, since these features were learned for different tasks, the authors fused them with the original clip features to create a more powerful representation. The authors also discuss the importance of using PRELU instead of ReLU in the decoder, as it allows the model to learn from negative values in the latent features. The architecture is illustrated in Figure 4. The authors evaluate their model on two multimodal classification datasets, MAMI and Hateful Memes. The MAMI dataset consists of 10,000 memes for training and 1,000 for testing, with two subtasks, binary classification and multilabel classification. The authors focus on the latter, using a validation set of 2,000 samples. The Hateful Memes dataset, constructed by Facebook, contains 10,000 memes with binary labels. The authors pre-process the text data by removing URLs, non-ASCII characters, and punctuation, and resizing images to 224 by 224. The authors use a focal version of the distribution balanced loss to optimize the multilabel classification problem, which is particularly useful for imbalanced datasets. The loss function is defined in equations 5, 9, where the focal parameter gamma is used to adjust the importance of positive and negative samples. Overall, the authors propose a novel architecture that effectively leverages pre-trained models and informative features for multimodal classification tasks, and demonstrate its effectiveness on two challenging datasets. The authors propose a novel multimodal semi-supervised learning method, SemiMemes, which leverages a rebalanced weight mechanism to address class imbalance issues in multimodal datasets. The method is applied to the MAMI and Hateful Memes datasets, where it is compared to state-of-the-art multimodal semi-supervised and supervised learning baselines. The rebalanced weight mechanism is defined as RK_I equals P plus P, caret, gamma 1, ZK_I plus nu I, lambda B, where RK_I is the rebalanced weight, P plus and P are the positive and negative class probabilities, ZK_I is the logit of the model, gamma is the focusing parameter, lambda is the scale factor, nu I is the class-specific bias, B is the estimated bias variable, and kappa is the scale factor of B. In the experimental setting, the authors create labeled and unlabeled sets for training, with varying proportions of labeled data, 5%, 10%, and 30%. The Atom optimizer is used with an initial learning rate of 1e4, and the learning rate is reduced after each epoch using a step LR scheduler with different gamma scheduler values for each scenario. The authors compare Semi-Memes to several baselines, including CMMLCLIP, TIBVA, and HateClipPer. On the MAMI dataset, SemiMemes achieves higher weighted F1 scores on both validation and test sets compared to CMML-CLIP and TIBVA, with performance gaps decreasing as the labeled samples increase. On the hateful memes dataset, SemiMemes also achieves higher AUROC scores than HateClip in all settings, with smaller performance gaps. The results demonstrate the effectiveness of SemiMemes in multimodal semi-supervised learning tasks, particularly when dealing with class imbalance issues. The method's ability to leverage in-labeled data and adapt to varying labeled ratios makes it a promising approach for real-world applications. Furthermore, the authors highlight the advantage of SemiMemes in terms of the number of parameters, with significantly fewer parameters compared to HateClip. This research focuses on the development of a multimodal semi-supervised learning approach, named SemiMemes, which utilizes a combination of CROMAE and RAWNCOOK models to identify and classify misogynistic and hateful memes in low-labeled data settings. The proposed method surpasses other state-of-the-art models on 2 datasets, demonstrating its effectiveness in detecting harmful content. The paper discusses the prevalence of Internet memes and the need for sentiment analysis to censor harmful content. It highlights the difficulties of the annotation process and proposes a novel approach that leverages the vast amount of in-labeled memes on the Internet. The approach utilizes semi-supervised learning, which has been shown to be effective in various domains such as image and video retrieval and emotion recognition. The research also provides an overview of deep semi-supervised learning, emphasizing its importance in dealing with limited labeled data. It references various studies on multimodal learning, including Visual BERT, which is a simple and performant baseline for vision and language tasks. Moreover, the paper discusses the Hateful Memes Challenge, a competition aimed at detecting hate speech in multimodal memes. It references the Hateful Memes dataset, which contains a collection of memes with annotated labels for hatefulness and offensiveness. The findings of Memotion 2, a workshop on multimodal fact-checking and hate speech detection, are also discussed in the paper. This workshop aims to advance the state-of-the-art in multimodal fact-checking and hate speech detection by providing a platform for researchers to share their work and collaborate on new methodologies. The paper concludes by emphasizing the importance of identifying and classifying hateful memes to ensure a safer online environment. It highlights the potential of the proposed approach, SemiMemes, in mitigating the difficulties of the annotation process and leveraging the vast amount of in-labeled memes on the Internet. The provided pages present a comprehensive literature review of recent works in multimodal learning, focusing on sentiment and emotion analysis of memes, visual models, and semi-supervised learning frameworks. The authors cite 26 research papers, highlighting their contributions to the field. The first set of papers, 2023, concentrate on meme analysis, including detecting harmful memes and their targets, dataset creation for sentiment and emotion analysis, and visuolingual metaphor analysis. These works demonstrate the importance of multimodal approaches in understanding memes, which are increasingly prevalent in online communication. The subsequent papers, 2426, explore semi-supervised learning frameworks for punctuation prediction in conversational speech, multimodal semi-supervised learning, and comprehensive semi-supervised multimodal learning. These works showcase the effectiveness of semi-supervised learning in handling limited labeled data and improving model performance. Notable among these papers is the work by Radford et al. 21, which introduces a method for learning transferable visual models from natural language supervision. This approach has significant implications for multimodal learning, enabling models to learn from diverse data sources. Another key contribution is the development of distribution balanced loss for multilabel classification in long-tailed datasets, 25. This work addresses the challenge of imbalanced datasets, providing a novel solution for improving model performance in real-world scenarios. The author's thorough review of these papers underscores the significance of multimodal learning and semi-supervised approaches in tackling complex tasks, such as meme analysis and visual model learning. By synthesizing knowledge from these works, the authors provide a comprehensive foundation for future research in these areas.